Over the last 3 nights, over 100,000 of you have been working hard, scouring an unexplored area of Mars.
And your efforts have paid off. You have made an incredible discovery on the surface of the Red Planet, and we'll be revealing all tonight.
I'm Brian Cox, he's Darrett O'Brien, and this is the final night of Stargazing Live.
Welcome back to a very foggy Jodrell Bank Observatory. So foggy we can actually hardly see the big dish behind us here. So really not a great night for stargazing. It was the third and final night of this year's Stargazing Live. Thank you so much for all of your emails, all of your photographs and all of your questions.
Yeah, we have some remarkable viewer photographs that I want to show you. This one is the Orion Nebula, of course. We saw it on the first night, I think, when we detected water in it with the Mark II radio telescope over there. But this is the picture. I want to give you some details. It's taken with a 4.5-inch reflector, so a small telescope, but 26 30-second exposures. This was taken outside last night at Jodrell with a really small telescope. This one, California Nebula. Do you know why it's called the California Nebula?
I've had a couple of guesses at this, but is it because it's broadly the shape of California?
It is. It's imaginously named. It was taken by James Dyson in Warrington, Cheshire, again on the 9th, which is yesterday, isn't it? I think it is.
Yes.
Yeah, and this is a emission nebula constellation of Perseus. And this one, I think, though, is the jewel in the crown in many ways. It may not look like it. It's actually, we now know, a comet. But the reason that it's the jewel in the crown is because we now know. This was discovered, or the photograph was taken by a Nick Howes, and he was in the States. But actually, the Fawkes telescope worked with a school in Buckinghamshire, Hazelmere School, to look at this and try and make sure to identify it formally as a comet. On Monday night, the stargazers at Hazelmere School worked with the Fawkes telescope. This is now a comet, so that's a genuine discovery. Now, as we mentioned, we have made some very interesting discoveries also on the surface of Mars. So Chris Lintott will be back later in the programme to reveal all.
Now, there's much more to stargazing than just these TV shows. There are over 500 stargazing events taking place up and down the country for you to get some hands-on with astronomy.
Yeah, and I've got some pictures because I want to show you what everybody's been doing. So here's one. This is the Canterbury Star Party. Again, I've written down all these details because they're wonderful. There's 1,200 guests turned up to Canterbury on Tuesday the 8th. And this is Fran Scott actually showing how to make rockets with a vitamin tablet. This is the Eden Project, the Star Party there. This is quite 1,500 guests. 1,500 guests on the 8th of January in the sultry, warm Mediterranean dome. And then finally, this one, which was sent in. That's nice. That was, where was that? That was in Birmingham. That one on Wednesday. And this is people from Birmingham University explaining how gravity works. So I've got one last picture that was sent in. This was sent in by Private Eye.
Oh, come on. Come on.
There's Darrett O'Brien there looking very handsome.
Thank you very much. It's so much better than the Megabus Man, which is the traditional comparison.
Anyway.
To find an event near you, please go to bbc.co.uk/stargazing. Now, we will be later in the show, we'll be going to see how Mark got with that Herschel telescope. Now, one of the reasons we're excited about linking Herschel into all of this, of course, is that, among his many claims to fame, is that he coined the term asteroid. Now, that means star-like in Greek, which is very appropriate given what we're talking about tonight. In just 5 weeks' time, an asteroid 45 metres wide with a mass of more than 130,000 tonnes is going to pass between us and the moon, coming closer to Earth than some of our satellites.
Yeah.
Then in March, the comet Pan-STARRS will streak across the sky, followed in November by ISON. Some people are calling the comet of the century.
ISON is going to be fascinating. This is an image of ISON as it is at the moment, not particularly spectacular, taken on January the 9th, 2013 by Nick Howes, just a little blob. ISON, though, is potentially going to be what astronomers call a great comet. It's going to pass by very close to the sun. It's actually going to graze the sun, about 750,000 miles over the sun's surface on just Boxing Day, in fact. And then if it survives that encounter with the sun, because that's close to the sun, it could break up. If it doesn't, it's going to sweep out. In January 2014, it could be one of those comets. You know those kind of medieval tapestry comets that you see sweeping across the sky? It could look like that. And it should be a naked eye object in the autumn sky as well as it nears the Earth.
That's fantastic.
It's quite remarkable. And we're all going to pass through the tail of that a little later in March, and it may give us a meteor shower.
That's fantastic. Now, we've getting questions from lots of people. April Hagan, for example, is one of the people who asked, what is the difference between asteroids, comets and meteors? It is one of the things I think you constantly have to keep explaining. We did this on Science Club as well.
Yeah.
Comets are basically like large, dirty snowballs.
Yeah.
Yes, they're icy with some rock mixed in as well.
That's the key thing, and they come from distant regions of the solar system. We're going to see a bit of that later on, actually. Regions called the Kuiper Belt and the Oort Cloud, icy snowballs, as you say. The asteroids from closer in between Mars and Jupiter.
Now, the comets are particularly spectacular. I think we've got some fantastic footage of various comets that we want to show here.
Oh, yeah. This one, I think this is is a beautiful shot from the International Space Station. That absolutely, you see, it looks like some kind of computer graphic. That's comet Lovejoy. Now, Lovejoy was discovered in December 2011 by an amateur astronomer, actually, Terry Lovejoy in Australia. And here it is passing behind the sun. Remarkable piece of footage. And here's another video. So this is, I think, from the Soho Observatory.
We can actually focus even closer in that sense. So
here we go. And there it's developing its tail. The thing about comets is that you tend to think of them streaking along with a tail behind them. In fact, the tail is blown by the solar wind, so the sun's heating the comet up. It's an icy snowball. You're getting gas and dust erupting at quite violent eruptions, actually.
So when it's moving away from the sun, it follows its own tail?
Yeah, so the tail will be always pointing away from the sun.
Asteroids are more like rocky fragments of planets?
Yeah. This is Eros, which is the first asteroid that we encountered in space. So this is not a video, it's real footage from a spacecraft that visited it. It's about 34 kilometres long, which is about the size of the thing that if it hit us, it would be the size that killed all the dinosaurs, the mass extinction about 65 million years ago. Now, it doesn't cross the Earth's orbit at the moment. It crosses Mars's orbit, though. And it's thought that because it continually crosses the orbit of Mars, it could be perturbed by Mars. So that thing could be a threat to us in several million years, but not at the moment. It's still a fascinating thing. And we actually landed on the surface of that asteroid.
And then when we talk about things like meteors and meteoroids, they're just about things in space which interact with our atmosphere. For example, meteors are when they burn up. One question we get a lot of time is about meteor showers. What do we pass through?
So we've got some video of the Geminids. Now, the Geminids are the meteor shower. You've just missed it, actually, this year. It's a December meteor shower. Very regular, always the same time. The reason for that is that the Geminids were created by a comet. They are the remains of the tail of a comet. Now, if you think about what a comet does, it orbits the sun. The periodic comets orbit around and keep coming back. So they'll leave an ellipse of debris, and that'll just sit there in orbit around the sun in the place where the comet tracks around. And the Earth passes through it at the same point in its orbit every year, because it's the same place in space. And that's why you always see them coming from the same place. And that's how meteor showers are named. It's named the Geminids because it looks as though it's coming from the constellation of Gemini, because we're passing through that comet's tail, the ancient bits of the comet.
So one thing we want to talk about is the big asteroid that's coming our way very soon. It's called asteroid 2012 DA14. On Friday, February the 15th, it's going to pass within 35,000.
Oh, here it is.
We put them out there. That's how close this is going to come. It's going to be between us and geostationary orbits.
Yeah, so these are our satellites, our communication satellites. So the green blobs you see there. And you see this thing's going to come well within the orbit of the geostationary, the weather satellites.
And it's going to pass on the 15th of February. Don't be worried, but I would say this is going to be the even more pressurised Valentine's Day, so do something really good on the 14th of February. How do we work out stuff like that?
It's going to miss us by a mile. Don't start those rumours.
How can we be so sure that this trajectory is right and that it really isn't going to hit us? To find out, Liz Bonnan is at the NASA facility responsible for tracking the movements of objects heading in our direction, and she's standing by for us now.
Thanks, Dara. Welcome to Goldstone in the Mojave Desert. This is the Mars Antenna, part of NASA's Deep Space Network, one of 3 70-metre dishes that are located around the planet and that maximise the network's power. Now, I'm inside the base of the antenna right now, and presently it's tracking the New Horizons mission to Pluto, but scientists also use it to track asteroids. Now, Marina Brozovic is one of the NASA scientists that does that work. Marina, how exactly does tracking an asteroid work?
It's actually really simple. Radar is like a flashlight. You point it to the asteroid and you bounce on some microwaves. This allows you to get its location very precisely, and as we do this day after day, we can significantly improve its orbit.
Now, you were working till the wee hours of the morning last night tracking Apophis, which has made the news all over the world because scientists in 2004 thought it's going to hit us in 2036. What is the latest? You've been looking at it all night.
Well, we've been tracking it since late December, and what you're seeing here are really the images from this morning.
So is that Apophis right there?
What you're looking into, this is a 300-meter diameter object that is 14.5 million kilometers away, and we have the detection. So radar data that we collected over the past couple of weeks have completely excluded any chance of impact in 2036.
2-0. We're safe.
That is, yes.
No
that
need
is
to
correct.
worry anymore. That's good news.
Furthermore, actually, we can now precisely predict its trajectory decades into the future.
Okay, fantastic work. Now, as well as just tracking to a certain orbit, you can also get really good resolution from these objects. This is Tutatis, a stunning image.
Yeah, well, this is a prime example of what radar can do. Yeah. What you're looking into, so this is 4.6 kilometer long asteroid that at a time was 7.5 million kilometers away from Earth, and we're getting 4-meter resolution. So 4-meter resolution allows you to resolve surface boulders. That's how good it is.
As that.
That is how good it is.
Technology. Thank you so much, Marina. Now, scientists are also getting a better idea of the composition of asteroids with their latest work, and what's clear is that there are many more different types than previously thought. So Amy Mainzer, another NASA scientist that specializes in tracking asteroids, taught me how to make my own.
We've got asteroids that are solid lumps of metal. We've got asteroids that are rubbly, like this pile of dirt here. And in fact, why don't you take some of this dirt and just spoon it into the bowl?
Okay, so step one, all asteroids will have some type of dirt.
Yes, that's right. So you've got silicon in here, you've got magnesium, iron, nickel, all kinds of heavier elements.
And that's going to be sort of the basic constituent of most asteroids. So we're going to take some of that water there and just pour it in. We're going to make a nice big mess. One theory about why there's so much water on Earth is that some arrived here aboard comets and asteroids. But that's not the only familiar substance found in them. Let's take some of this molasses. So that represents this organic material. All the organics, carbons, hydrogens, things like ethane, methanol, stuff that we see in minor planets. How much? That's pretty good. Nice. This one's carbon rich. This one. This is right. Now we need a squirt of another ingredient that's been found in the remains of asteroids that have landed on Earth: ammonia. Ammonia. Yeah. Then we add our final ingredient: dry ice. At minus 78 degrees centigrade, it'll mimic the freezing conditions of the solar system. Just sprinkle that in there. We're going to really freeze it up good. Let's take a look and see what we ended up with here. Oh, that's amazing. That's what we got. And in true asteroid style, it's beautifully irregular. It is not completely round. It kind of looks through space. Oh my goodness. This asteroid is a very particular kind, a randomly active main belt object, a Rambo, would you believe? And as you'd expect, it is special. We've actually discovered in the last maybe 10 years or so this very unusual class of asteroid that actually becomes active. Active in what way? Occasionally, these things exhibit huge clouds of gas and dust coming off at the surface. And we think that what happens is when the sun hits the objects, if we use this bright lamp here to represent the sun, what we think happens is that a smaller asteroid may strike the surface and scrape off some of this dirty outer layer, and it may expose some of the ice underneath the surface. Look at that jet just coming out from a tiny little hole, and you can't see any of the ice exposed there. That's right. So this is a really good example of what we think happens. If we were orbiting the sun, what it would look like is that this object would start to have a big tail around it and a big halo following it. Almost 2 years ago, the Hubble Space Telescope photographed a Rambo, which grew a tail when it was heated by the sun, and just there is its X-shaped impact scar. But closer to home, what's the worst that could happen to the Rambo we've made? I mean, this is a good-sized lump of rock, but bearing in mind its size relative to the Earth, how can this really cause that much damage? Right, well, something this small obviously can't. But if something were, say, the size of a building, like maybe 30 or 40 meters in diameter, it would be large enough to make it through the Earth's atmosphere. Now you've got something that can cause a great deal of damage, because if it's traveling at, say, 10 kilometers a second or more, it packs an enormous punch. And Amy has now joined us at Goldstone. Amy, you use space telescopes to find out about potentially dangerous asteroids. Tell me about the NEOWISE project.
Right, so the NEOWISE project is a space telescope that used infrared light to discover and track near-Earth asteroids.
Yeah.
And that's important because infrared is heat. We're sensing heat with this. So that gives us an idea of the size of the object. We can tell the difference between something that's, say, really large but dark, like a piece of coal, or something that's much smaller but highly reflective.
Okay.
So getting the size is important for understanding the hazard. Now with NEOWISE, we observe a sample of the near-Earth asteroid population and then use that to extrapolate what's really out there.
Okay, so what have you come up with?
Good news. Okay, so for objects that are larger than about a kilometer, now these are the planet busters, like the dinosaur-killing asteroid. 90% of these have been found.
That's good news, but where are the other 10%?
Well, we don't know where they are.
Yet. Okay.
And there's another piece of not so good news, which is that for objects larger than about 100 meters, we only have discovered about 25% of those.
Okay, and they can cause quite substantial damage too.
Absolutely, yeah, those are not good either.
Okay, so it's clear that you need to continue this surveying work to find out where the others are.
That's right, we still have a lot more work to do.
Okay, what happens if a big one's coming at us, Amy? What can we do?
Well, ideally, we will find an object, before, say, 20 to 30 years before it's going to have a close approach or possible impact with the Earth. If we have time like that, we can design mitigation strategies that would, say, for example, use explosives to push the asteroid aside or break it into pieces, or maybe even devise technology to gently tug it out of the way.
Tug at it? How do you do that?
Either gravitationally, by using a spacecraft to pull on it, or even attaching a solar sail, perhaps.
Astonishing technology. Thank you so much, Amy. Come back to us when we talk about the missions that are teaching us more about asteroids and comets than we ever knew before. See you soon.
Thanks, Liz. Well, standing by right now on our live blog is Don Yeomans. He's head of NASA's Near-Earth Objects Department. He's the man who has to keep the President informed if an asteroid is heading our way. What do you say to the President? Mr. President?
Great news!
So need you to take your questions at bbc.co.uk/stargazing.
Lots of people are asking where these objects originate from in space, and we have a top-of-the-range model for you here.
Yeah.
All of the asteroids that we will ever encounter come from one thin strip here, don't they?
Yeah, essentially everything comes from three places. The first one I want to talk about is the asteroid belt. We've got an animation that shows the asteroid belt. It sits between Mars and Jupiter, and it's the green area there. So every point here is a mapped position of an asteroid. So this is what it looks like. You can see the inner planets, including the Earth, orbiting around there. It's still a bit of a mess, which is why we get impacts. But the asteroid belt is packed with rocky objects, including this one. This one is called Vesta. And this is a fascinating world. I've got an image of it here. It's quite a big rock, so I don't want to give the impression that they're all very small. It's about 350 or 400 kilometres in diameter. And the remarkable thing about Vesta, we're going to talk about it later, is I've got a piece of it here. You see that big crater on the top? This came from there. The mystery will be revealed later on. It's beautiful, isn't it?
That's fantastic.
Step out all the way past the gas giants, we come to here. This is the Kuiper Belt. Now, this is a region of icy, rocky objects, more icy than anything else. This is where Pluto lives, actually. So the ex-planet Pluto. It was demoted because it turns out it's one of many objects of large size in the Kuiper Belt, and then hundreds of millions, billions of objects that are smaller, icy snowballs. We're on our way to Pluto at the moment. This is a picture of the spacecraft that's there. It's called New Horizons. It left in January 2006. When it left, Pluto was a planet. When it got to about there, Pluto got demoted. But by that time, it was too late to stop. It's on its way. Actually, that makes no difference to the science of the mission. These are the best images we have of Pluto now. They're from the Hubble Space Telescope. It is extremely cold out there. We don't really know a lot about Pluto other than we have these images.
And it's because it's so cold that it's mainly this is where we're seeing all the ice.
That's it. So we have frozen ice. It's about minus 200 degrees Celsius out here.
And what's further?
And then finally, you step out into this region, the far reaches of the solar system. This is called the Kuiper Belt. And I've got a picture of the the Oort cloud. This is more of a spherical cloud.
This is all in a plane, as we know. This is all the disk of the solar system.
But this, as you can see on that picture, is rather more spherical. It is a vast collection of large and small lumps of ice and rock. Remarkably, it stretches out about a light year, we think. It's a quarter of the way to the nearest star. Many of the comets, in fact, most all of the comets that we see, come from either the Kuiper Belt or the Oort cloud.
Okay, so there are all these objects in motion above us, but we're in motion as well. So in order to work out what things we're in danger of hitting, we need to know precisely where the Earth is at any time. So how do we work that one out? Part of the answer lies in the southern hemisphere sky.
The Southern Cross is an iconic constellation in the southern sky. It even features on the Australian national flag. It was by interpreting patterns of stars in the sky like this that we began to make sense of our cosmic surroundings. Here on Earth, it's easy for me to work out my position relative to the objects I can see, to understand my place in this world. But if you're an astronomer, you have a problem, because all you can see are little points of lights in the sky. And certainly for the early astronomers, they knew nothing more than that. To make progress, people began to make maps of the night sky in as much detail as possible. This is an early star chart of the southern sky, published in 1801 by the German astronomer Bode, and it is a two-dimensional representation of the position of the stars. So here's the Southern Cross, and if you follow it up in an arc, you get to the bright southern star Alpha Centauri. But 200 years ago, the way these maps were made meant their accuracy was limited. When Bode made this map, he did it by hand. He looked at the sky and transcribed the positions of the stars onto this piece of paper. It's a huge opportunity for human error in that process. But in the late 19th century, a new technique allowed astronomers to achieve real precision: photography. If you have a photographic plate and a telescope, the marks on that plate are not made by the human hand. They're made by photons of light that have travelled from the stars themselves across hundreds or even thousands of light years to register their position on the map. By fitting a camera to a telescope, the accurate positions of thousands of stars could be recorded in a single exposure, something astronomers hoped would help them determine our place in the universe. In 1887, the decision was taken to map the position of every star that can be seen in the sky with high precision. That was a project that took, in fact, until the mid-1940s. That's an incredible commitment. It's like building a cathedral. And much of the southern sky was mapped from here, Sydney Observatory. And this is one of the photographic plates that was used to construct what is now known as the astrographic catalogue. It's an exposure which took just over 6 hours, and you can see a huge number of very faint black dots on the plate. Each one of these black dots is a star, and their positions were measured and transcribed into here, the astrographic catalogue. You can see that this is 1893, January 20th, and column after column documenting the positions and brightnesses of the stars on this photograph. So what we have here is a perfect representation of the positions of the stars in the sky from Sydney on January 20th, 1893. 750,000 stars were recorded at Sydney Observatory, and the results were combined with surveys made at 19 other observatories around the world, creating a single, huge catalogue of the stars across both hemispheres. For the very first time, astronomers had an accurate record of our position relative to 4.5 million stars. And that's helped us to measure another intriguing characteristic of the stars with great precision.
In the 1990s, these measurements were repeated, this time by a satellite, the European Space Agency's Hipparcos satellite. And what was found was that for at least some of the stars, their positions changed by an appreciable amount.
This slow drift is called proper motion. It's unique to each star, and because it takes years to become apparent, comparing recent satellite data with the astrographic catalogue has given us the most accurate ever record of this phenomenon. The reason for this relative movement is that all the stars in the Milky Way are orbiting around the centre of the galaxy, but each at its own particular speed. And today, looking even deeper into the universe, it's apparent that it's not just stars that have their own unique motion. By looking out beyond the stars of the Milky Way, we found that all the galaxies in the universe are moving relative to each other as well. So we're part of a group known as a local group, 43 galaxies bound together in the same way that the stars are bound together in the Milky Way. And that group itself is moving actually roughly in that direction towards the constellation of Centaurus to something called the Shapley supercluster, which is a group of 5,000 galaxies or more, about 500 million light years in that direction. And we're travelling towards this enormous cluster of galaxies at over 500 kilometres a second. So what we've discovered over hundreds of years of astronomy, making precision measurements of the sky, is that everything in the universe is moving relative to everything else. We've learned that the stars and galaxies are all taking part in a vast cosmic dance, which we can now plot with incredible accuracy, thanks to hundreds of years of mapping the night sky.
So we've all these objects which seem in stable orbit around the sun in the solar system. So why do some of them suddenly lurch out and go on these crazy journeys that might collide with us?
The answer, as with every answer, lies with mathematics. And to explain that, we've got Tim O'Brien. Tim, the mathematics of orbits.
Yeah, I mean, you remember that all these objects that are orbiting around the sun, they're doing that under the influence of Newton's law of gravity, an inverse square law, where the force depends on the distance. And it turns out that there's only 4 possible shapes of orbit that they can have. And the really neat bit of maths here is that those shapes are actually defined by slices through a cone, which explains why we have these 4 bits of cone in front of us. And depending on what angle you slice through, you get a circular orbit, an elliptical orbit, a parabolic orbit, or a hyperbolic orbit.
Now, so all these things we can see on the table are in essentially elliptical orbits. Some of them are more circular than elliptical, but basically in general, everything
It's
is.
exactly what you presume. They go round and they come back and they go round and they come back. That would be a sound orbit.
So the most common orbits are the elliptical and the hyperbolic. Actually.
Now, a hyperbolic orbit now is open. So basically, if something gets bumped into a hyperbolic orbit, that's going to go around the same place it was going around before, but it's going to go around and shoot off.
Yeah.
And it never comes back, so it heads off out there and it's gone out into interstellar space, potentially.
And the difference between these is essentially to do with energy and something called angular momentum, but we don't need to go into that. Essentially, what can happen, let's say we're in the Kuiper belt, and something has a gravitational interaction. One of these icy snowballs gravitationally interacts with Pluto, let's say, one of the bigger objects in the Kuiper belt. It will change the energy of that object. And what's that going to do? It's going to change the orbit, because these shapes are defined partly by the energy. So what can happen is one of these things can be perturbed, so it begins a journey into the inner solar system. Halley Comet, which I think actually came from the Oort cloud, let's be specific about it, it's not about letters. That comes in, it's still in an ellipse though, isn't it?
It is, yeah, it's in an ellipse. It's got a period of 76 years, so it comes back every 76 years.
So it's quite an elongated ellipse.
So it could have jumped from a circular orbit out in the Oort cloud to some sort of elliptical orbit that it's in now.
Because of an interaction. But actually, the Oort cloud is interesting, isn't it? Because it's so far out, as we said, up to a light year, that in fact many of the perturbations come from passing stars, which is quite a remarkable thought. They're very weakly bound to the sun, because, as Tim said, the force drops away. Well, he didn't say it, actually, we can say it now. The force drops away as the square of the distance.
A star comes back, it bumps it by passing, and then it heads off on this new journey.
Yeah, well, these hyperbolic orbits are the kind of interesting ones, the troubling ones in some ways, because you don't see them coming, because they come in and they have such an orbit that they swing around the sun once, and disappear off.
So they're in some sort of orbit. Something
Disappear off.
perturbs them, bumps them. Brian is going. I've been waiting to do that for 3 years now.
Hyperbolic.
It's gone, and we'll never see him again. He'll disappear off in his hyperbolic orbit. Maybe someday he'll pass you to find out if there's clear skies where you are tonight, because we want you to start looking up at the sky, of course, all through this. For the final time this series, let's cross over to Susan Powell in the BBC Weather Centre.
Evening, Dara. We're up against it this evening thanks to quite a lot of cloud piling into the UK. To the east of the UK, we've had a weather front which has hung around for much of the day today, and I'm afraid it's not going anywhere in a hurry, so that's going to obscure the skies here. Further west, another front that's fizzling out. We'll lose the rain, but the cloud is going to stick around. Between the two, though, hopefully a few clearer spells across the northwest of England and for northern Scotland in the next few hours. But my top picks are the clearer skies this evening into the early hours of tonight. I think we'll be behind our weather front in the west. We should see clearing skies to the southwest of England and South Wales, and give it a couple of hours now, and I think Northern Ireland will be looking almost crystal clear as we go into the small hours of Friday. More information, though, as ever, on the BBC Weather website. But for now, it's back to you.
Thanks, Susan. It sounds like a nice place to be, Northern Ireland tonight. Crystal clear skies. Anyway, our astronomer Mark Thompson has been building a modern interpretation of William Herschel's 20-foot telescope. This was the instrument, remember, that he used to make some of the most vital discoveries about the Milky Way, including the two moons of Uranus, the Shakespearean Titania
And Oberon, isn't it?
Oberon, I think. Was it?
Yeah, I think it is, yeah. Somebody will correct
That's
us.
what you get for ad-libbing. Anyway, in a tribute to his pioneering work, Mark has been trying to recreate that telescope.
Over the past 3 weeks, I've been working with the local community in Derby in a crack team of experts. We've had to make changes to Herschel's plans to keep everyone safe, but we've remained true to his principles. So far, we've built the supporting structure. Big no. Now, we just have the small matter of making the actual telescope. In Herschel's telescope, right at the bottom of the tube was a piece of lovely polished metal to reflect the light from the stars. It was shaped and positioned to focus the light towards the top of the tube. And here, Herschel would have stood on this viewing platform and stared down a barrel through an eyepiece. So this is our telescope tube, and we're going to put a mirror up this far end. So light comes down the tube, hits the mirror, bounces back up the tube, and then all the way up to the top into this special adjustment we've made. We've had to cut a portion of the tube out where the eyepiece is going to go, and hopefully we'll see some stunning views of the sky through it. Do you want us to push?
Not too much, but I'm in the middle of it.
Now we just need to get it up into the cradle, and engineer Chris Hill is on hand to supervise.
See? Oh, what's that? 290mm. That's planned.
It's finally starting to look like a telescope. Meanwhile, inside the university workshop, Chris is putting the final touches to the mount for the mirror, and instrumentation expert Dr. David Brooks is here with the missing piece. Chris, it's arrived. Finally, the mirror has arrived. We're using a modern glass mirror in our telescope.
Oh, wow.
Herschel would have used a piece of metal, and that would have easily tarnished. Even though he polished it for hours, it still wouldn't have been very reflective.
I only had 63% reflectivity.
Right.
This has got over 99% reflectivity.
So Herschel would have been blown away by this, probably.
Yeah, this would have been his Christmases. Yeah.
The mount for the mirror has a set of screws on the back so that the angle of the mirror can be adjusted. Now we can collimate the telescope and align the mirror, so the light from the stars is reflected through the eyepiece. Should we try and put it in then? Let's try it. I think the time's come, isn't it?
Yeah. You got screws, I've got the bolts. Just yours, mate. Back a bit, there. Don't move.
The first step is to cover the opening with a large sheet of paper. For the next bit, Herschel would have probably used a candle, but we're going to use a laser pointer. The light travels through a small hole in the paper, down the tube, and hits the mirror at the bottom. It's then reflected back at an angle to hit the paper again. Now I need to guide Chris to adjust the mirror until the reflected laser light moves into position where the eyepiece will be. Chris, if you can tilt the bottom towards me, so bring that out a bit away from you.
So,
Yes.
gotcha. Okay, can you see it moving?
Yes, keep going, Whoa. Spot on. How's that looking to you now? That looks perfect. That looks excellent. Yeah, that's perfect, mate. Well done. Cool. So this laser beam is actually simulating starlight, and it's bouncing back out of the tube, which is where I need to look. Now you can see if I spray this, where the beam is coming out of the tube, just where it needs to be, which shows to me that the telescope is nicely collimated, so we're ready for some clear skies.
Well, after all that work, the time has come. To reveal the telescope, let's cross over live to Mark now at the University of Derby.
Well, there's a fantastic atmosphere here at Derby. We've got our own Herschel Quintet playing some of Herschel's own music because, of course, he was a very accomplished musician as well as astronomer. We've got the children from the Markeaton School who helped decorate the telescope. We've also got the members of the Derby Astronomical Society who've helped plan the thing, and I know they're itching to get their hands on it. So hello, guys. Now, it's taken us 5 weeks and hundreds of man-hours. It's got a 20-foot long tube and it weighs in at just under half a tonne. It is Stargazing Live's Herschel telescope. Now, it is the most amazing piece of kit. It's got a crank to turn the whole telescope so it moves up and down. The whole structure moves around so that you can access any part of the sky that you want to. It's the most amazing piece of kit. Now, hopefully, if it stays clear, we might get a chance to look through the telescope. Now, with me is Professor Alan Chapman, who helped realise the design of the telescope. Now, Alan, what do you make of it?
This is absolutely remarkable. It's a tremendous realisation of Herschel's telescope using scaffolding and modern equipment, and I've never seen anything like it before. Even to the chaps pushing it around. Probably Herschel used sailors, I suspect.
He used exactly the same. Yeah. Now, of course, we've used the same tube dimensions, the same mirror diameter, but we only had a drawing to be able to work from. We had no measurements. It took him a year, and he did it in 5 weeks. You know, that is quite incredible, isn't it?
Well, of course, we knew where we were going, and we also know what we're looking at. He didn't. To him, it was entirely experimental and a brilliant piece of inspired engineering. Also, too, I think other factors came in as well. Herschel was a skilled worker with his hands, a mirror figurer, a designer, and of course, he employed carpenters to do all the heavy work for him. And he saw the heavy work in terms of planing boards and so on. Yet, Herschel was a skilled musician, a string player, a keyboard player, and I think all of those skills were necessary to the manipulation and adjustment of that instrument. He did complete code.
I'm going to have to stop you there, Alan. I'm really have to stop you. So thanks to the guys from the Derby rugby team to move it. After all that hard work, I'm really looking forward to actually looking through the telescope. It's still cloudy here in Derby. It's foggy in Derby as well, but with a bit of luck, it may clear up. So do come back to us a bit later on tonight, and we'll see if we can recreate the images that Herschel saw.
Oh, hopefully we will. Now, we've been talking about asteroids and comets in a sort of faintly doom and gloom way. Of course, we will be struck by large objects from space. It's happened all through history. But it isn't necessarily a bad thing, because without these kind of impacts, our world might not be the place that we know today.
If you want to see one of the best preserved meteor impact sites here on Earth, you need to travel to the Barringer crater here in Arizona. Craters just like this can be found all over the solar system, the battle scars of a long history of cataclysmic impacts. Most are the result of one period, around 3.6 billion years ago, when the whole solar system was turned upside down. And it was all to do with the combined gravitational force of our two biggest planets, Jupiter and Saturn. We now believe that the giant planets formed much closer to the Sun than they are today. Their orbits drifted for hundreds of millions of years until Jupiter and Saturn fell into a regular pattern. Once every cycle, the two planets aligned, creating a gravitational surge that played havoc with the orbits of all the planets. Neptune was catapulted outwards and smashed into the ring of comets surrounding the solar system, with dramatic consequences. For 100 million years, the solar system turned into a shooting gallery as a rain of comets ploughed through it. Millions of comets were scattered in all directions, peppering the planets. It was called the Late Heavy Bombardment. It created many of the craters we see throughout the solar system today. It left scars all over our moon. And it had a lasting impact on the Earth as well. The only impact craters we see on Earth today, like this one in Arizona, were made much more recently, but they reveal the scale of these impacts. Now today, impacts like this are relatively rare, although they will happen again. But during the Late Heavy Bombardment, the Earth was hit by thousands of objects with sizes far in excess of the object that made this crater, and the environment was changed radically and dramatically. But those changes weren't necessarily catastrophic, because it's now thought that a significant amount of the water in the Earth's oceans was delivered by the impacts of water-rich comets and other objects during the Late Heavy Bombardment. And that means that impacts could have played a key role in the development of life on Earth. Before the Late Heavy Bombardment, the Earth was a barren rock. Afterwards, it supported the oceans that would become the crucible for life. Without the water delivered in the Late Heavy Bombardment, life on Earth may never have evolved. It's quite a thought that all this may have been caused by the violent gravitational pull generated by 2 orbiting planets.
Joining us now is meteorite expert Dr. Richard Greenwood from the Open University. We've already seen one of your fantastic samples already.
Yeah, so we talked about Vesta.
That's a meteorite Cameldonga, and it's from Australia, and it's got a special composition that we know matches Vesta. And it's a fantastic story. It's a meteorite conveyor belt. Basically, 1 billion years ago, a meteorite smashed into the southern hemisphere of Vesta, liberated these asteroids, which we call Vestoids. They gradually drifted into the 3-to-1 resonance with Jupiter, and then were fired on an Earth-crossing orbit. And it's a real conveyor belt because we have basically 10 times as many meteorites coming from Vesta as we have from either the Moon or Mars.
I think that's remarkable, and it's all to do with this gravitational interaction with Jupiter, throwing these things our way at quite a rate.
Now, this is iron, isn't it?
That is, and that's a brilliant one. If you pick it up, you'll see that it's actually 3 times denser than a rock that you find in your garden. That's because it's pure metal, and it's the core of an asteroid that melted. When it melted, the metal sank under gravity and formed a core. And we used to think that those were quite young, but in fact, that's one of the oldest objects in the solar system. And the reason for that is because at that time they had a very high concentration of very short-lived radionuclides, particularly one called aluminium-26. And that would have been formed in a supernova. It's a supernova that preceded the formation of the solar system, and it's probably the shockwave from the supernova which actually triggered the collapse, which formed our solar system.
So short-lived, you mean it's what's the half-life?
Well, short-lived, it's a 700,000 years half-life, so within 2 million years, which is a really small length of time, it would have all have gone.
So these are unstable atomic nuclei, relatively unstable,
that's right,
made in a supernova explosion that coalesced to form the early solar system, heated the asteroids up.
That's it.
And that's why you get the iron sinking to the centre of the asteroid.
You said it was very old, but it's not the oldest thing you brought.
Well, no, it isn't actually, because what we actually have from some very primitive meteorites, this one here called a Vuna, which fell in Tanzania, when you take that and you put it into acids, you can concentrate grains which actually predate the solar system. We call them pre-solar, and that's some of them there. And in there are diamonds, silicon carbide, and graphite, and they came from some of the stars that predated the solar system.
What I'm holding in this file is older than the solar system.
It's older than the solar system.
And what's the current age of the solar system, the best age?
The best age is 4,567 million years, so 4,567 million years.
And that's older
and that's even older.
And we know that, so the story of the origin of the solar system is a supernova went off, a shockwave came through this gas and dust, caused it to collapse. And pieces of that shockwave, so this is from outside the solar system, from the supernova,
exactly,
it's rattled through and got trapped in these meteorites.
And it did, yeah.
Absolutely beautiful.
But as well as studying meteoroids that have reached Earth, technology now allows us to get up close and personal with asteroids and comets whilst they're still in orbit. Let's go back to Liz in NASA's Goldstone facility to hear more.
Thanks very much, Dara. Goldstone and the rest of the Deep Space Network have communicated with some truly remarkable missions, getting us very close to asteroids and comets that are speeding through space. Amy, if we can talk about a few of them. Stardust. I mean, sampling from the coma of a comet. That's incredible.
It's amazing. The Stardust mission actually flew through the coma of the comet, and it stuck out a little plate that was sticky like flypaper. That actually allowed it to collect tiny pieces of the comet and bring them back to Earth for scientists to study.
And it's really given us a new window into the solar system because none of that material has changed for 4.5 billion years.
Exactly. It's very ancient material and very precious to study.
Sure. And the Deep Impact mission kind of does what it says on the tin.
Yeah, exactly. So Deep Impact is actually 2 spacecraft in one, an impactor spacecraft and an observer that was loaded with cameras. When the spacecraft got close to a comet, they separated. The comet smacked into the impactor spacecraft while the observer watched and allowed us to see the inside of the comet being gouged out.
And so what did we learn from that material when it was analysed?
It was actually a really surprising result. So it turns out that this particular comet was more dust than water ice. That was surprising. And also, the inside is a lot of empty space. It would actually float if it were in a bath of water.
So these missions are teaching us a lot more about, what truly categorizes a comet and an asteroid. I mean, the two lines are kind of more blurry than we thought.
Exactly. They have a lot more in common than we've previously thought.
Yeah. And then the Dawn mission, of course, which sent an orbiter to mighty Vesta in the asteroid belt.
Yeah, that's right. The Dawn mission has been orbiting Vesta, one of the largest asteroids in the asteroid belt, and it's returned spectacular images that have really allowed us to see the turbulent history that's happened to this asteroid.
Yeah.
In fact, there are 2 giant impact craters that have gouged off the south pole of the asteroid, and there are giant scrapes that are even larger than the Grand Canyon.
They really are teaching us so much. Thank you so much for joining us, Amy. It's been a pleasure
to
see you again. And Dawn is actually on its way to Ceres, the biggest rock in the asteroid belt, 950 kilometers in diameter. And actually, it's been reclassified as a dwarf planet now. It will reach it in 2015 and will begin its exploration then. Back to you guys at Jodrell Bank.
Thanks, Liz. Well, of course, that space that surrounds our planet isn't just filled with natural objects. It's also filled with stuff we put up there.
Yes, so much stuff that there is a pileup waiting to happen. In a quiet corner of Hertfordshire is a radar tracking station that's used to monitor the movement of objects 2,000 kilometres above the Earth. There are lots of things we've got up there. 1,000 satellites, nearly 20 telescopes, and 1 space station. But there is also a lot of junk, affectionately known as space debris.
Space debris is effectively all the stuff in space that we no longer use or need. It could be dead satellites, it could be dead rockets, it could be fragments, pieces of electronic circuits, pieces of paint from the outside of a spacecraft. All these things are up there floating around.
The final frontier is packed with rubbish, literally. There's everything from an astronaut's glove, that one stayed in orbit for a whole month, to particles of urine flushed from early spacecraft. There are bits of rockets left by the Apollo missions. There are even 32 nuclear reactors that used to power satellites.
So this shows you a simulation of what we can actually see in orbit. It ranges from debris very close to the Earth into orbits where, for instance, TV satellites are operating on a geostationary orbit. So these range in size from something the size of a mobile phone all the way up to a space station.
All these objects mean we're getting tight for space in space.
What we've realised over many years is that although the universe is potentially infinite, the space around the Earth is actually very finite.
But the problem isn't just that it's crowded up there, it's also dangerous. All these objects are hurtling about at over 25,000 kilometers per hour. It's like a cloud of flying bullets.
An object moving at that speed has a very high energy. So, for instance, a pound coin in orbit around the Earth has the same energy as a minibus travelling at 100 kilometres an hour. Now, if that object was to strike a spacecraft, it would destroy it.
In 1983, a chip of paint collided with the space shuttle. The impact was enough to crack its 1.5 centimetre thick windscreen. In 2009, a US and a Russian satellite hit each other. Both were completely destroyed and created up to 1,500 new bits of junk. And it can only get worse. In 60 years, we've gone from no man-made objects in orbit to an estimated 35 million. And the worry is that areas of space that we rely on to send satellites for navigation, weather forecasting, and even TV will soon become no-go areas. Currently, there is no working answer, but all sorts of plans are being hatched. From sails that would slow an object down so they fell back to Earth, to giant balloons that would inflate to help put the brakes on. But the UK's largest space company has come up with the Space Harpoon. Astrium in Stevenage is better known for building satellites that get sent to space. But engineer Jamie Reed's job is to use his harpoon to drag them back to Earth.
So here we've got a harpoon that we're going to fire. It goes into the barrel inside the protective chamber. I'm going to put some goggles on.
The harpoon uses compressed air rather than explosives to fire, which is a little safer for space.
We're ready to fire now. Turn the firing switch on.
Sadly, there's no countdown.
Just fire.
At the moment, Jamie is test firing his harpoon into pieces of actual satellites. It's early days, but when complete, the harpoons will have a spring-loaded barb and tow cables. If the system works, the harpoon will be mounted on a satellite that will chase down space junk, harpoon it, and tow it back towards Earth, where it will burn up safely in the atmosphere. Of course, this only works with larger objects, but in orbit, big objects are just thousands of smaller objects waiting to happen. Something has to be done, and this could be the best thing. But until somebody can enforce an intergalactic dump drop litter campaign, the research has to continue. Now, here's a vivid demonstration of the problem. This is kindly lent to us by the National Space Centre. It's a panel from the LDEF satellite. That's the LDEF satellite. It's actually that panel, that exact panel there. That's when the LDEF was being brought out of orbit in 1989.
Pictured out with the shuttle underneath.
Isn't it fantastic? Onto the space shuttle. This was in orbit for 6 years, and when they brought it down, they saw all this scoring here. And all of these are impacts of micrometeorites. Micrometeorites are smaller. They're invisible to the human eye.
Yes, they're just specks of dust. I think they're travelling it between something like 8 or 9 kilometres a second and up to 30 kilometres per second. So an immense amount of energy being dissipated, and that's why you see the plasma burn.
And their plasma burns. That's how hot it is. And if you lift it up, you can actually see. Yeah.
There we are. So this is the spacecraft hull, and you see there, let's take that one. That's a hole, and that's a hole, and that's a hole, and you can see the dent in there.
These
absolutely
minuscule piece of dust.
Dangerous place. Dangerous place. Anyway, back over to Mark in Derby now. Last time we saw him, he'd unveiled our version of William Herschel's 20-foot telescope, but have they been able to actually observe anything with it? How are you getting on, Mark?
Unfortunately not. It is quite amazing standing here on this platform, just like Herschel did all those years ago. Now, of course, Herschel did it much like me in the damp English weather. I'm much safer than he is because I've actually got a harness to make sure I don't fall off. But there are times when observers of similar telescopes have actually fallen off those platforms. But unfortunately, we can't show you any pictures. But it is quite incredible to think that Herschel spent many, many years observing the night sky with the British weather to contend with, and he mapped most of the sky that he could see from his observing point. Now, we did get some clear skies a few nights ago, and we managed to record some images of some things in the sky. The first picture we managed to get was Jupiter. Now you can see in this shot Jupiter moving very gracefully across the screen, and that's caused by the rotation of the Earth because the telescope doesn't actually have a drive system, so you can't see the object being tracked. We got a picture as well of Albaria, which is a beautiful binary star system in the constellation of Cygnus, which you can see in the centre of the Summer Triangle. We got a picture as well of the Trapezium star cluster in the centre of the Orion Nebula, and that looks really quite stunning. You can see the nebulosity that the stars form from. We got a final image of Uranus, which of course Herschel did discover, not with this telescope, but with a slightly smaller one. And you can see there is a very slight distortion, which was caused by the orientation of the optics in the telescope. So he would have had to have contended with these really quite poor images. Now, we can't show you anything live tonight, which is a real disappointment, but it is great to follow in Herschel's footsteps. And without great astronomers like him, we wouldn't have learned much about the universe and the night sky that we can see now. It's great, of course, that we can leave this telescope to the residents of Derby, so hopefully in years to come they can enjoy the night sky view just like Herschel did all those years ago. For the last time for me, it's back to Dara and Brian in the studio.
Thank you very, very much, Mark. They are beautiful images, and that telescope will be, I think, in the University of Derby for the next 3 years anyway. So there'll be a lot more observing done with it. And this week, you two have been doing your own pioneering scientific work thanks to our online Mars exploration experiment. We asked you to study sections of Mars' surface, looking for unusual features, and the results were incredible.
You know, I often spend a lot of time looking at the sky going, isn't that wonderful, isn't that amazing, and using all these overly hyperbolic adjectives. In this case, they're absolutely appropriate. Dr. Chris Linton is back with us. This is, I think, wonderful and amazing.
Well, real science in 2 days, which is good. We haven't slept much because more than 100,000 people have helped us explore an area about the size of Holland we're up to.
It was Switzerland, didn't we?
That's right, yeah, we're working our way up because people are still there, there's still images, and we found some great stuff.
Yeah.
So we were looking at the Antarctic region of Mars and these strange fans, which we think come from material suddenly erupting from underneath the surface of Mars. And we had this idea that it was to do with ice that was under the surface that was being heated up. But
that's a time lapse, basically.
That's right, yeah. Sorry,
that
was a year on Mars, as put together by Planet4.org users.
And so at some point of the year, in the Martian spring, let's say, these things suddenly erupt as the planet heats up.
Well, that's what we now know. I can tell you for sure, because we only find these around March in the Martian calendar. If Mars had a calendar like Earth.
Discovery.
That's right, and we see them, they happen first close to the equator, and then they head closer to the poles, and we thought they were rare, but look at this. This whole region of ground would have erupted underneath your feet, so don't go there. Don't go there in the spring.
And I wanted to just fade in that artist impression that we showed back on
Right,
Tuesday.
so this is what we think is going on.
But we discovered that.
That's right.
That's the remarkable thing about it. Our viewers discovered that is what's happening. It's a new scientific...
We know when it happens, we know where it happens, and we now know it's much more common than we thought it was. And that's all because people used pattern recognition skills to look at these images.
But there's more than that, isn't there?
There's more than that, because a good scientific experiment always leaves you with more questions. We've no idea what this is. So this is a type of terrain that I haven't seen before. It's got these strange angular features. And what's weirder is these move from year to year. So they march across the surface. No idea what this is. It's something to do with ice escaping from underneath and going up into the Martian atmosphere. There'll be people working on this for years.
That's just wonderful.
We have more time in the show afterwards and back there to discuss this.
I've got to say, right, I pledged a pint to someone. Tweet at BBC Stargazing. Tell us what that is. What do you think that is? The best tweet, we'll announce it at the end of Back to Earth. I will buy you another pint. Yes, because I'm very excited about that. What is that?
Yeah, the other guy's still waiting for his pint, by the way, so don't get too excited.
Get overexcited.
Before we go, there's just time to say goodbye to Liz, who's been in NASA for us all week. How's it been?
Okay, 30 seconds to us. Thanks, Dara. You know, thanks, Dara. It's been such a privilege to meet all the people behind so many awe-inspiring endeavours. And what struck me most is how every single mission seems just impossible on paper. So I'm not sure what impresses me more, the fact that they're able to dream up crazy schemes like lowering a rover onto Mars using a sky crane and sampling comets as they hurtle through space, or the fact that they're able to make those ideas a reality. And they're always thinking ahead, you know. By the mid-2020s, there's talk of putting a man on an asteroid. A few decades after that, a man on another planet. It's really such an exciting time for space exploration here. But sadly, it's time for us to say goodbye to everyone here at NASA and to you back home at Jodrell Bank. Good night from NASA.
Good night, Liz, and thank you for wearing your telescope hat specially for the occasion. Apologies for going to you slightly too early. Don't forget there are hundreds of Stargazing live events happening up and down the country for you to take part in. Details are on the website, bbc.co.uk/stargazing. Don't forget about our Star Guide, made in conjunction with Open University, info on how to get that should be running across the screen at the moment. We're going to be back here in a second, but do you want to wrap up in any way?
I do. I think genuinely that the discoveries on Mars, they're real scientific discoveries. These. Chris was telling me just off camera that there's going to be a paper written. I believe that if there is a scientific paper written, everybody who contributed to that will have their name on the paper. So all you people who logged in, if that turns into a scientific paper, you will be a published author.
Share of the Nobel Prize. There's actually cash money to be made out of this. We will see you in a few minutes back here. But
next year, undoubtedly.
Yeah, of course. Who'd cancel this? Is great. Because it's a comet. We want to catch the comet.
Over the last 3 nights, over 100,000 of you have been working hard, scouring an unexplored area of Mars.
And your efforts have paid off. You have made an incredible discovery on the surface of the Red Planet, and we'll be revealing all tonight.
I'm Brian Cox, he's Darrett O'Brien, and this is the final night of Stargazing Live.
Welcome back to a very foggy Jodrell Bank Observatory. So foggy we can actually hardly see the big dish behind us here. So really not a great night for stargazing. It was the third and final night of this year's Stargazing Live. Thank you so much for all of your emails, all of your photographs and all of your questions.
Yeah, we have some remarkable viewer photographs that I want to show you. Now, this one is the Orion Nebula 14. It could be one of those comets, you know, those kind of medieval tapestry comets that you see sweeping across the sky. It could look like that, and it should be a naked eye object in the autumn sky as well as it nears the Earth.
That's fantastic.
It's quite remarkable. And we're all going to pass through the tail of that a little later in March, and it may give us a meteor shower.
That's fantastic. Now, we've gotten questions from lots of people. April Higgins, for example, is one of the people who asked, what is the difference between asteroids, comets and meteors? It is one of the things I think you constantly have to keep explaining. We did this on Science Club as well.
Yeah.
Comets are basically like large, dirty snowballs.
Yeah.
They're icy with some rock mixed in as well.
That's the key thing, and they come from distant regions of the solar system. We're going to see a bit of that later on, actually. Regions called the Kuiper Belt and the Oort Cloud, icy snowballs, as you say. The asteroids from closer in between Mars and Jupiter.
Now, the comets are particularly spectacular. I think we've got some fantastic footage of various comets that we want to show here.
Oh, yeah. This one, I think this is a beautiful shot from the International Space Station. That absolutely... you see, it looks like some kind of computer graphic. That's comet Lovejoy. Now, Lovejoy was discovered in December 2011 by an amateur astronomer, actually, Terry Lovejoy in Australia. And here it is, passing behind, of course. We saw it on the first night, I think, where we detected water in it with the Mark II radio telescope over there. But this is the picture. I want to give you some details. It's taken with a 4.5-inch reflector, so a small telescope, but 26 30-second exposures. This was taken outside last night at Jodrell with a really small telescope. This one, California Nebula. Do you know why it's called the California Nebula?
I've had a couple of guesses at this, but is it because it's broadly the shape of California?
It is. It's imaginatively named. It was taken by James Dyson in Warrington, Cheshire, again on the 9th, which is yesterday, isn't it? I think it is.
Yes.
Yeah, and this is a emission nebula constellation of Perseus. And this one, I think, though, is the jewel in the crown in many ways. It may not look like it. It's actually, we now know, a comet. But the reason that it's the jewel in the crown is because we now know. This was discovered, or the photograph was taken by Nick Howes, and he was in the States. But actually, the Fawkes telescope worked with a school in Buckinghamshire, Hazelmere School, to look at this and try and make sure to identify it formally as a comet. On Monday night, the stargazers at Hazelmere School worked with the Fawkes telescope. This is now a comet, so that's a genuine discovery. Now, as we mentioned, we have made some very interesting discoveries also on the surface of Mars. So Chris Lintott will be back later in the programme to reveal all.
Now, there's much more to stargazing than just these TV shows. There are over 500 stargazing events taking place up and down the country for you to get some hands-on with astronomy.
Yeah, and I've got some pictures because I want to show you what everybody's been doing. So here's one. This is the Canterbury Star Party. Again, I've written down all these details because they're wonderful. There's 1,200 guests turned up to Canterbury on Tuesday the 8th. And this is Fran Scott actually showing how to make rockets with a vitamin tablet. This is the Eden Project, the Star Party there. This is quite 1,500 guests. 1,500 guests on the 8th of January in the sultry, warm Mediterranean dome, I mean. And then finally, this one, which was sent in. That's nice. That was where was that? That was in Birmingham. That one on Wednesday. And this is people from Birmingham University explaining how gravity works. I've got one last picture that was sent in. This was sent in by Private Eye.
Oh, come on. Come on.
There's Darrow Breen there, looking very handsome.
Thank you very much. It's
It
so
was
much
like-
better than the Megabus man, which is the traditional comparison.
Anyway.
To find an event near you, please go to bbc.co.uk/stargazing. Now, we will be later in the show, we'll be going to see how Mark got with that Herschel telescope. Now, one of the reasons we're excited about linking Herschel into all of this, of course, is that among his many claims to fame, is that he coined the term asteroid. Now, that means star-like in Greek, which is very appropriate given what we're talking about tonight. In just 5 weeks' time, an asteroid 45 metres wide with a mass of more than 130,000 tonnes is going to pass between us and the moon, coming closer to Earth than some of our satellites. Then in March, the comet Pan-STARRS will streak across the sky, followed in November by ISON. Some people are calling the comet of the century.
ISON is going to be fascinating. This is an image of ISON as it is at the moment, not particularly spectacular, taken on January the 9th, 2013 by Nick Howe, just a little blob. ISON, though, is potentially going to be what astronomers call a great comet. It's going to pass by very close to the sun. It's actually going to graze the sun, about 750,000 miles over the sun, over the sun's surface on, and just Boxing Day, in fact. And then if it survives that encounter with the sun, because that's close to the sun, it could break up. If it doesn't, it's going to sweep out in January 20.